the colligative properties. And we're going to do this in lab today. We're going to make some ice cream. Why do we add salt to the ice cream? Not to the ice cream. Salt to the ice in the ice cream maker. We do it to make it colder. So salt lowers the temperature at which a saltwater solution freezes. So it will freeze at about -10 degrees Celsius instead of 0 degrees Celsius. And what is really kind of trippy, and we'll see in lab, we're going to have our ice, and we're going to take the temperature of just the ice as it's melting, and that'll be about 0. And then we'll pour salt on the ice and let that mix up a little bit, and you can watch the thermometer go down. We didn't put it in the freezer. We didn't add, it had ice in it. We didn't add any ice or anything. We just added salt, and it gets colder. It's really, Pardon me?
Does it take long for the temperature?
No, not long at all. Just, a minute or two. Yeah, it's pretty crazy. So this is called freezing point depression, lowering of the freezing point. And this is one of several colligative properties. And colligative properties depend on the number of particles that are dissolved, not the kind of particle. It's just the number of the particles. And we'll see that colligative properties for electrolytes are a little bit different than for non-electrolytes. Because if you have 1 mole of an electrolyte, it could form 2 moles of particles, or 3, or 4, depending on the ratio of ions in it. And so that will affect the freezing point and the other colligative properties more. I'm going to come back to this one. No, I better not. I'll just go straight through. Okay, so vapor pressure lowering. We talked about vapor pressure. So here we have a liquid in a closed container, and we have evaporation, and we have condensation, and they come to a dynamic equilibrium, and there is a pressure, a partial pressure to this solvent in the gas state. If we add a solute to this liquid, making it a solution, those solute molecules are going to interfere with the evaporation of the solvent molecules because they're going to occupy some of the surface of the liquid, right? And so that's going to make it harder for molecules to evaporate. So the rate of condensation will be larger than the rate of evaporation until they reach a new dynamic equilibrium, and now the vapor pressure is less. So adding something to the liquid causes the vapor pressure to be lower. So that's the maybe easier to understand method or explanation. This one is really kind of trippy. And this is something you could try at home too if you have some patience. So here you've got a beaker with pure solvent, say water, and here is a concentrated solution. So a bunch of salt dissolved in water. And you stick this in a closed container. So this is like a cake plate, right? But these beakers are open. I don't know how long it takes. It's not going to be instant. You probably better wait a day or two. But what you'll find is that the level of the liquid in the pure water beaker goes down, and the level of liquid in the solution beaker goes up. So that seems like, wait, what? Water moved from this beaker to that beaker. Yep, that's what it did. So, of course, this water is going to evaporate, right? And it's going to be bopping along like gas molecules do, and then it's going to crash over here, but the rate of evaporation here is less. And so this will gradually accumulate more of the solvent. So we saw this with the aquarium with the salt water and the fresh water, and take the divider out, and they mix naturally, right? Well, they will mix naturally here as well. Any questions? Of course, there's a law that quantifies that. It's called Rollett's Law. And this is the person whose quote was at the beginning of the chapter. So the vapor pressure of the solution is going to equal the mole fraction of the solvent times the partial pressure of the pure solvent. And this has to be all at the same temperature. Vapor pressure is directly proportional to the amount of solvent. So the vapor pressure lowering, or the change in the vapor pressure, is equal to the mole fraction of the solute times the partial pressure of the pure solvent. Now this is a little bit different than that, and we could go through the derivation, but I don't think anybody wants to. So calculate the vapor pressure at 25 degrees C of a solution containing 5.3 grams ethylene glycol and 285.2 grams water. Vapor pressure of pure water is 23.8 torr. So this one is asking us to calculate the vapor pressure, not the vapor pressure lowering. So we want this top equation here. The vapor pressure of the solution is the mole fraction of the solvent times the partial pressure of the pure solvent. So here the solvent is H2O. I'm sorry, this is not the partial pressure of the solution. Will be equal to the mole fraction of the solvent times the partial pressure of the pure solvent. So we need mole fraction. The mole fraction is going to equal the moles of water divided by the total moles. Should be the moles of water plus the moles of the ethylene glycol. I'm going to call him EG. So we have to calculate some moles here. 285.2 grams of water. Divide that by molar mass of water. So 15.827. Oops. 15.8269 moles. And then the ethylene glycol, 55.3 grams of EG. I was tempting to ask Siri, but I don't know that I trust her. So there's 2, 4, 5, 6 hydrogens in there times 1.008, and there's 2 carbons and 2 oxygens. So 62.068. It's the mass of ethylene glycol per mole. So 0.89096. So the mole fraction is the moles of water divided by the moles of water plus the moles of the solute. 0.94671. That's the mole fraction. Mole fraction always has to be between 0 and 1. So here we have the mole fraction times the vapor pressure of pure water .5. Any questions? If the solute is volatile, if it evaporates, then it will also contribute to the vapor pressure of the solution. So we can talk about an ideal solution, which obeys Raoult's law at all times. The total pressure of the solution should equal the partial pressure of each of the parts. But there are also non-ideal solutions that do not follow the law. So this is a graph showing ideal behavior. So this red here is the partial pressure of component A. This is increasing as the mole fraction of A increases. And here we have the vapor pressure. So the vapor pressure of B decreases as the mole fraction of A increases. And this total vapor pressure is just the sum of both of those. But if we have strong interactions between the solute and the solvent, then that's going to decrease the evaporation of the solute and the solvent, and it's going to cause all of these lines to curve down. If we have weak solute-solvent interactions, the solute and solvent are kind of ready to get away from each other, and so these lines will bulge up. They don't follow the law. We're not going to do that. We're not. So freezing point depression. So the vapor pressure affects the freezing point and the boiling point. So we find vapor pressure lowering occurs at all temperatures. And so here's our phase diagram. And we see that adding a solvent, making the solution, will decrease the pressure. And it will decrease the pressure here as well. So it moves this line over. Normal freezing point is where we have this fusion line going between solid and liquid at 1 atmosphere. So that gets moved over here. The melting point is lowered. Melting point, freezing point, same thing. And the boiling point becomes elevated. This is another thing I used to have a hard time remembering. Was it freezing point depression or freezing point elevation? They move away from each other. So the freezing point goes down, the boiling point goes up. The higher gets higher and the lower gets lower. And this is why we don't put pure water in our radiators. Adding antifreeze, which is typically ethylene glycol, increases the boiling point of the fluid. It also decreases the freezing point. So it has to get colder before it'll freeze. And if you live in Minnesota, that matters. You don't want your radiator freezing solid. So the change in freezing point or freezing point depression is equal to the molality of the solution times a factor. It's a freezing point depression constant. And that is for the solvent. They use molality here instead of molarity because we are talking about things happening at different temperatures. So we want a concentration unit that's going to stay the same. So these constants we would just look up in a table. Here's various solvents. Here's water. This tells us the normal freezing point and the freezing point depression constant. It also gives us the normal boiling point and the boiling point elevation constant. So calculate the freezing point of a 2.6 molal aqueous sucrose solution. So we need the freezing point depression constant for water, 1.86. .86 degrees Celsius per molal. So the change in the freezing temperature is equal to the molality times the freezing point depression constant. So the molality is given to us here, 2.6 molal. We multiply by the freezing point depression constant. The molalities cancel out. 2.6 times 1.86, 4.836. It didn't break. And that'd be 2 sig figs. Is that the answer? No. So what I did is I calculated the freezing point depression, the change in the freezing point, not the actual freezing point. So then I need to take this change and apply it to the actual freezing point. So, we call this delta T, but that's not a final minus initial kind of delta, unfortunately. So this is what I would recommend, is just kind of make yourself a little thermometer. Okay, here's where the water freezes normally. And so freezing point depression, it's going to go down this much, right? So this is my new freezing point, and this difference is 4.836 degrees Celsius. So the freezing point is negative 4.8 degrees Celsius. I think it's easier to, just have a thermometer, a little loop up there, to avoid getting confused on whether you should add or subtract. Any questions? Now what we're going to do in lab today when we make the ice cream, we are going to measure the freezing point depression. We're going to measure the temperature at which the ice is freezing before we add the salt and after we add the salt, and we're going to find that difference, right? And the freezing point depression constant is the same. And so we can use the change in the freezing point to calculate the concentration of salt in our salt water. And that's what we need for lab, so let's just stop right there.